Okay, so last time we looked at calculations, 4 examples of calculations of strong acids and strong bases. But in those examples, we mainly looked at the area where the acid HA was our only species contributing to our pH. And we also looked at an area where HA is negligible and only water is contributing to the pH. And we said that when the concentration of the acid is very low meaning 10 to the minus 8, that's it, we only consider water. And when the acid is significant enough, then only it exists in water and contributes to the pH. But we still have this area here, okay? And what about this area? This is the area where we said that we have both the acid and water are contributing to the pH of the system. And so in that case, we said that we have to use a quadratic equation. And I'm just going to do, first of all, a type of calculation where you would just have memorized the quadratic. And let's go right into it. This is an extra problem. It's not part of your sheets. And there isn't any one single problem which looks at this area. It looks like some people don't cover it or something like this. In any case, let's look at this. Calculate the pH of nitric acid solution that has a concentration of 5 times 10 to the minus 8. So if we look at this concentration, we can clearly say that this concentration is greater than 10 to the minus 8, but this concentration is less than 3.2 times 10 to the minus 7. Okay? And therefore, this area is right in that middle grounds where I have to consider both the acid and the autoionization of water. Both give me H3O plus, and my pH has to be determined from both reactions. And to be honest with you, I really would tell you that I hate to memorize, but memorize it. All I can say that this is not so bad, because you could say x squared, which is H3O plus, minus Cx minus Kw equals 0. And for an acid, this is a minus sign and a minus sign. And we're going to derive it for you. I am going to derive it in just a moment. So once you do this calculation, so what do I have? I put my concentration in. Let me just clear this. So we have x squared minus C here would be 5 times 10 to the minus 8, which is my concentration. H3O plus is x, minus 10 to the minus 14. Actually, very simple. Of course, very simple because we can use our calculators, and you have become experts at that, haven't you? Solve for x, and my x is simply H3O plus, at which point you would say minus log of this H3O plus is going to be 6.89, and so your answer is C in this case. And now for the derivation. Where did this quadratic equation come from? Okay, and every time before we derived the actual pH, or the concentration of H plus, or any quadratic that I use, so why aren't we doing it here? We are. And here we go. We have an acid HA reacting with water to give you H3O plus. That's my first acid dissociation. And generally, we used to take care of only that. But in the presence of autoionization of water, where the autoionization of water is significant and contributes some H3O plus in the solution, which is not negligible, Then there is H3O plus coming from both equations. Okay, so how do I solve for the pH? Well, I find that the easiest way is just to first consider only the equilibrium of the acid of the water, the autoionization of water. So we're only looking at this reaction. And we're going to say that since this acid, you know that this is a strong acid, right? We've decided we're doing calculations of strong acids. So their Kas are very, very high, and usually we don't even give you a Ka. But they are so high, the Kas, or they're high, greater than 1 at least, that this dissociation of the acid takes place way before the water dissociation even starts, or that the first reaction is advanced relative to the second. Okay, so if it's advanced, what I can consider then is that my initial concentration in the autoionization of water is not necessarily 0 for H3O plus. I can now consider that the concentration of H3O plus is the amount that is coming from the acid. So the acid originally dissociates, let's say gets a concentration C for H3O plus, C for HA, for A minus. And then you just transfer this H3O plus is already in solution before water even starts to dissociate. And then water starts to dissociate, okay? And now when water dissociates, we have a change plus x due to the dissociation of water. And at equilibrium, we will say that H3O plus concentration will be the concentration of the original acid plus the x, which is the amount attributed from the water, and the concentration of OH minus is simply the x. So it's as simple as that. And then, of course, this is the autoionization of water equation, so therefore I need a Kw is H3O plus times OH minus. Of course, water here, we never put a concentration for him. Okay, so now substitute very directly. The concentration of H3O plus is simply C plus X. The concentration of OH minus is simply X. Now there's two ways about going this. Of course, you should factor out in the X value. And you should notice that the X is actually OH minus. Now you could either get this X and then now you have OH minus and then get H3O plus, then get pH. Or, like I said, I'm deriving this quadratic. The derivation of the quadratic comes about by saying that the X is simply Kw divided by H3O plus, right? Because OH minus is Kw divided by H3O plus. Now substitute in, instead of X, put Kw divided by H3O plus, and instead of the X value here, also do that. Oops. So just substitute for the X, Kw divided by H3O plus, and what you end up getting is this quadratic equation. Of course, you have to multiply. You do some mathematics here, multiply everything. You get rid of all the Kws, they're gone, one of them is gone, and then you multiply by H3O plus on the denominator, and it's easy to derive in case you forget it. I still recommend that you simply memorize it, but in case you forget it, just use the autoionization of water, and for the H3O plus, use the concentration of the acid that you have originally in the solution, which is actually quite a dilute concentration, right? There's also another way to derive it, and that's using the electroneutrality principle. So again, we have two equations taking place. Both are contributing to the H3O plus concentration. If I I can write down the species, but the species right away are from this equation. Just look at the equations and there's your species, okay? I don't really have to write down species are blah, blah, blah. The equations tell me what the species really are. And now from these species, these compounds, let's put all the positives on one side and all the negatives on the other, and thus to make the solution electrically neutral. So what are the positives? Well, H3O plus is on one end, because look at, I'm trying to look for anything that's positive. Okay, H3O plus is positive, so that goes on the positive side. And, well, this H3O plus is the same as this one in solution. There isn't any difference, so that's done. All the negatives on the other side, and so take the negatives. I have A minus, that will go on this side, and OH minus as well. So the negatives on one side and the positives are on the other. And we're clearing. Now, this is a little bit not confusing actually. What is OH minus? We're going to try to put everything in terms of H3O plus. So any type of, if I have OH minus, can I convert it to something with H3O plus? And if there's something that could be a constant, I will put it as a constant. And so, of course, you would know, and you already know, that OH minus can simply be Kw divided by H3O plus. What about A minus? Well, A minus is actually simply the concentration of the original acid, because we know that the acid, when he dissolved, he gave me a C amount of H plus and a C amount of A minus. Now, when I was a student, I never understood, I couldn't get into my mind why I don't put also C here. Well, I was young then. Well, because the H3O plus doesn't just come from this acid, it also comes from the dissociation of the water. So this is actually a variable, okay? So it's not constant because the dissociation of water is not constant. It's at equilibrium. And so I can't put C here, okay? Anyway. Now factor everything out, multiply everything by H3O plus on both sides, bring everything to one side, and you get the quadratic equation, which you are supposed to use under those conditions, okay? It's as simple as that. Both of them are simple. I like the first way method because, I could see what's in solution more, but both are very simple to derive in case you forget the equation. Now, what about for strong bases? Within the same range of concentration as well, in this case, where the concentration of the base is greater than 10 to the minus 8, but it's less than 3.2 times 10 to the minus 7, that is when we have a strong base with concentration C and we cannot neglect the dissociation of water. And so both equations, the dissociation of the base and the autoionization of water, are needed to calculate my pH. And both of these equations contribute OH minus into the solution. And they release OH minus. Now, in the same analogical way that we did the acids, we can do this with the base, okay? So, as well, the dissociation of the strong base, this one, and this is a metal, right? Because strong bases are metal hydroxides. I could always get whatever, if this is C, then this is going to be 0 at the end, and this is going to be C and C. And so I'm just going to erase here. So the concentration will be whatever concentration I have in solution. Okay. Now, like I said, this is analogical. Ooh. Initially, I don't have 0, 0 for H3O plus OH minus for the autoionization. Instead, I have already some OH minus with a concentration C coming from where? coming from the OH dissociation. Okay, so that's that C. And then, all right, present. Okay. And then, sorry about that, the water starts to dissociate, and finally, Kw will be H3O plus times OH minus, and instead of H3O plus, I simply have X, transfer through, and for the OH minus, now I have C plus X. I really like this because for me it's very logical. How much H3O plus do I get? It's only from water. What's the OH minus? It's from the water and from the base. Very simple, very easy to think about. And this time H3O plus is, X is H3O plus, and therefore I am done. Factor the X in the inside and put H3O plus instead of X, and you get the quadratic for a base. Guess what? It's very similar to the quadratic for the acid. Again, this is H3O plus squared plus C, H3O plus minus Kw. So again, this is like an X squared plus Cx minus Kw equals to 0. Really nice, because the only difference from the other one is this plus sign. So if you memorize one, you have the other. The way I remember it is that acids have a lower pH, so that's a negative, and bases have a higher pH, so I put a positive, okay? Get a higher number. Anywho, once you have, of course, here the H3O plus concentration, don't forget that in the end you still need a pH. So once you get the H3O plus from a calculator, then you get the minus, then you have to say minus log of that number, which is your pH, okay? Great. Of course, there is also the method of by electroneutrality. I'm going to go through it. I'm more of a fan of the one I just discussed, but anyways. For the electroneutrality, again, we have these equations, and therefore those are my species. Put all the positives on one side, negatives on the other side. So my positive is the metal, my positive is the H3O plus, and my only negative is OH minus, and this OH and this OH are the same. Now, again, I want everything in terms of one variable, so I'm going to choose H3O plus as my variable. So I'm going to convert this OH minus to Kw divided by H3O plus. And the metal is actually a constant concentration, which is the concentration of that base that I originally put in, because the metal only comes from that one source. And now here it says, well, multiply everything by H3O plus, put everything on one side, and voila. You also get the same answer. So both are really easy methods to follow in case you forget this equation, okay? Of course, it's a lot faster if you just remember the equation, but you know what? I hate to memorize. I'm not sure about you. Clear? All right. So we're done for this part.